Okay, so the focus for this lesson is to look at Euler's number. Euler's number is represented by the letter E. The E, well, it doesn't stand for Euler, but anyway, is an irrational number which has special properties in mathematics. This is what you can write in. E, because it's an irrational number, it means it's a number with a decimal that goes on forever without any particular pattern. So E is equal to 2.71828, and it keeps on going without pattern and without end. That's what makes a number an irrational number. It is often used as a base. You know what I mean by a base in maths? Like 2 to the power of 7, 2 is the base. 6 to the power of 4, 6 is the base. So it is often used as a base when modelling growth and decay problems. I'm going to pause the video while you write. And I want you to read or to write just that top bit there. Don't worry about the base function. Just write growth decay problems in nature and other context and leave it there. And then I'm going to show you a video. It's done. Okay, so we just looked at a video which explained why E is such an important number in mathematics. They didn't talk about this in the video, but it does tend to, when we create models using E to the power of something, it does tend to fit a lot of natural context and other contexts as well. So it's used quite frequently. So you can start writing now. The base function is y equals e to the power of x. When I say base function, I mean the fundamental function, not base as in the base is e. So y equals e to the power of x. And just briefly, we're going to look at natural logs on Monday, but its inverse is called the natural logarithm. Okay? So I wanted to get this language out now, but we're going to come back to it on Monday. So we know that logs and exponents are inverses of each other. We know that already. Logs and exponents are inverses of each other. So it shouldn't be too much of a stretch for me to fill in the gap here. Log base e of x is how we would write the natural logarithm function. Log base e of x. But it is such a common logarithm. There's two really common logarithms. Log base e is one of them. What's the other one? Yeah, log base 10. Log base 10 is so common that we don't tend to write the 10 in. We just go log of x. Why? Because it's so common. It's so common that we don't bother. It's like we don't bother writing the square root of 4 like that. 10, natural logarithms, because they are the inverses of e to the power of, and e occur, like models with e in it occur everywhere, like I said. 10, because it's the decimal system. One thing I found curious, because I never saw this before Wolfram Alpha. You know what Wolfram Alpha is, the website Wolfram Alpha? Oh, well, if you don't know it, look at it at some point, because it's got a natural maths engine in it. So you type in expansions or expressions and whatever else, and it will do it for you and give you an explanation and stuff. But Wolfram Alpha, when it says log of 6, it means the natural log, but it writes log. But I don't think that's usual. So log base e of x, but it's so common that it is often written as, now you don't have to do it in chord cursive. I tend to, so it doesn't look like a 1. It is often written as ln of x. Okay, so that's ln x is how you would say that, ln x. So when you see ln x, it means the natural log of x. It literally means log base e of x. It just does. All right, so moving on. I'm going to do an example sketch, and I've got it in stereo there. And then you can go ahead and practice some problems as well. Because the good news is that apart from knowing what it is and roughly knowing the value is kind of important too, so it's roughly 2.7, the good news is it is just another base ultimately. It is, in terms of the way you graph it, you manipulate it, it's just another base. What you'll find is different is that rather than having an x-intercept, sorry, I'm just making an example up. Instead of having an x-intercept of, say, a y-intercept of, say, 3, your y-intercept might be e plus 2 or something like that. Okay, so it won't be a nice, neat number. It'll be an expression with an e in it. Let's have a look at that right now. So this is an example sketch. F of x equals e to the power of x plus 1 minus 1. I didn't draw the parent or the base graph in. You should know what a base graph of a to the x looks like anyway. So what we're doing now is we're going straight into a sketch, and we'll follow our usual methodology. So first of all, we'll go with shape. There's no reflection here, so we know the shape is going to be going up like that, right? Asymptote. What's the asymptote of this one? Good correction. Yes, y equals negative 1. Good. The start was minus 1, which is just a number. The asymptote is an equation. Y equals negative 1. I'll write that a bit more clearly so you can read it. Okay, what else do we have to do then? Yep. Is it going to have one? Yeah. So in your head, hopefully you can sort of imagine the graph is going to the left by 1 and it's going down by 1. So if it goes to the left by 1, it's still going to have a y-intercept. If it goes down by 1, will that give it an x-intercept or not? Yeah, it will. Again, if you can't do it in your head, that doesn't matter. Just go, okay, I know the asymptote's here. It's going to go like that. Okay, I don't know where that is, and I don't know where that is. Maybe it's like that. I don't know. But at least you get the idea there from your really rough graph that it definitely has an x-intercept and a y-intercept. Really rough, because you want to confirm it with numbers before you do a proper sketch. So let's do it. Let's do y-intercept first. That's what I tend to do. So y-intercept, that's at x equals 0. So we've got y is equal to 0 plus 1. Minus 1. Okay, so that is the point 0, comma, e minus 1. Good with that so far? So if e is about 2.7, then e minus 1 is going to be about 1.7. So we should expect a positive y-intercept. Let's keep going. X-intercept, which is at y is equal to 0. Okay, so at y equal to 0, 0 is equal to e to the power of x plus 1 minus 1. Oops. So e to the power of x plus 1 equals 1. What could we do from here? No, I wouldn't do ln personally. Yeah, I'd make the same base on both sides effectively, right? So I would be going e to the x plus 1. You can do this in your head, but e to the x plus 1 must be the same as e to the power of 0. Does that make sense? Okay, really common. You can do ln and stuff. If you ln both sides, that would work as well. So that gives me x plus 1 equals 0 by equating powers, and x equals negative 1. So that's the point minus 1, comma 0. So now we can see that this means it's going to cut through the x-axis on the left of the y-axis, and it's going to cut through the y-axis above the x-axis. So now we can graph it. I'll do a really quick graph. There's x, there's y. I'm going to put my asymptote in, which is negative 1. Oh, that was bad of me after I just told you not to say that. Which is y equals negative 1. And then I'll pop my graph in. I know that it needs to cut through here and here, so that's fine. I'm not going to put them in until I draw it though. That way I don't have to miss the spot. Like so. And then I'll label my points. So I will go, this point here is 0, -1. Oops. Try that again. -1, 0. And this point here is, I'm going to write it exactly, 0, E-1. And again, just in your head, keep track of that. E-1, that's like about 1.7 or so. Just keep a little loose track of it so you can sort of, know where to place it on your axis. And that's basically it. So you've got just a few questions to do here. We've got 10 minutes now, so you can start now, complete it for homework, and then we'll be right to work on natural logs on Monday.